Hello, sir. This is Mario Reddy, 19BCE1533. So, as you can see, today I'm going to talk about the PCA, Principal Component Analysis. So, let's get started with the topics what we're going to discuss. Here, as we can see, the first we're going to do the introduction and the objectives of PCA and terminology, algorithm, applications of the PCA, and conclusion. So, let's get started. So, what is PCA? It is a statistical procedure that uses an orthogonal transformation that converts a set of correlated variables to a set of uncorrelated variables. PCA is the most widely used tool in the exploratory data analysis and in machine learning for predictive models. Moreover, PCA is an unsupervised statistical technique used to determine or examine the interrelations among set of variables. It is also known as a general factor analysis, where regression determines a line of best fit. So let's move on to the next slide. Introduction. So as we can see here, the problem. Analysis of multivariate data plays a key role in data analysis, and multidimensional hyperspace is often difficult to visualize. Represent data in a manner that facilitates the analysis. And we can see here objectives of unsupervised learning methods. The first one is reduce dimensionality and score all observations. And the third one is cluster similar observations together. And we all know well-known linear transformation methods, PCA, factor analysis, projection, pursuit, etc. So coming to the again introduction to contradiction. So benefits of dimensionality reduction. So the computational overhead of the subsequent processing stages is reduced. Also, noise may be reduced. A projection to a subspace of a very low dimension is useful for visualizing the data. Moving to the objectives of PCA. So the main thing is principal component analysis is a technique used to reduce the dimensionality of the data set and also to identify the new meaningful underlying variables and also lose minimum information. So by finding the directions in which a cloud of data is stressed the most. PCA or Carhanian lower transform summarizes the variation in a possibly correlated multi-attribute to a set of two smaller number of uncorrelated components, principal components. So these uncorrelated variables are linear combinations of original variables. And mainly, the objective of PCA is to reduce the dimensionality by extracting the smallest number of components that account for most of the variation in the original multivariate data and to summarize the data with a little loss of information. And coming to the terminology. So here we're going to discuss about the variance, covariance, eigenvectors and eigenvalues and the principal components. So coming to the standard deviation. So average distance from mean to a point is known as the standard deviation. And variance. In the variance, we can see here standard deviation squared and one-dimensional measure. So here equals to variance whole square equals to summation of n and I equals to 1, x of I minus x bar whole square by n minus 1. So let's see how two dimensions vary from the mean with respect to each other. So yeah, here you can see the formula. Covariance of x comma y equals to summation of n I equals to 1 x of I minus x bar into yi minus y bar by n minus 1. So here covariance of x comma y is greater than 0. That means dimensions increase together. Covariance of x comma y is less than 0. That is known as 1 increases and 1 decreases. Covariance of x comma y equals to 0. Then dimensions are independent. So, and we can also see that here the terminology. Just a minute. I'm gonna just hide this. Yeah. So covariance matrix we're gonna see contains covariance values between all possible dimensions that equals to, as you can see, dimension of Cij by Cij equals to covariance of dimension I comma dimension j. Example for 3 dimension x comma y comma z always symmetric. So here C equals to covariance of x comma x, covariance of x comma y, covariance of x comma z as follows. Here covariance x comma x equals variance of component x. So coming to the eigenvalues and eigenvectors. Eigenvalues. Eigenvalues is the measure the amount of variation explained by each PC, and less than 1 indicates that PCs account for more variance than accounted by one of the original variables in standardized data. This is commonly used as a cutoff point for which PCs are retained. And coming to the eigenvectors. Eigenvectors provides the weights to compute the uncorrelated PC. These vectors give the directions in which the data cloud is stressed the most. So, coming vectors x having same direction as ax are called eigenvectors of A. And A is an n by n matrix. In the equation Ax equals to lambda x, lambda is called an eigenvalue of A. Ax equals to x equals to A minus lambda I into x equals to 0. So here you can see the calculate of x and lambda. So moving on. So principal component. So the extraction uncorrelated components are called the principal component, which is known as PC. So estimated from the eigenvectors of the covariance or correlation matrix of the original variables. The projections of the data on the eigenvectors, so extracted by linear transformations of the original variable, so that the first few PCs contains most of the variance in the original data set. So coming to the algorithm. So yeah. So we look for axes which minimize projection errors and maximizing the variation after projections. So here you can see n-dimensional vectors to m-dimensional vectors where m is less than n and transform from 2 to 1 dimension. Contradiction to the fact, preserve as much of the variance as possible. So here I'm going to explain a bit of myself. So steps further, let's discuss about the steps for PCA algorithm. So first thing, getting the data set. So firstly, we need to take the input data set and divide into two subparts, X and Y, where X is the training set and Y is the validation set. And representing data into a structure. So now we'll represent our data set into a structure such as we'll represent the two-dimensional matrix of independent variable x. Here each row corresponds to the data items and the column corresponds to the features. So the number of columns is the dimensions of the data set. So coming to the third step, standardizing the data. So in this step, we'll standardize our data set, such as in particular column, the features with high variance are more important compared to the features with a lower variance. So if the importance of the features is independent of the variance of the feature, then we'll divide each data item in a column with the standard deviation of the column. Here, we'll name the matrix as Z. So I'm coming to the fourth step. That would be calculating the covariance of Z. And after that, calculating the eigenvalues and eigenvectors. So, and the coefficients of these eigenvectors are defined as the eigenvalues. Coming to the sorting the eigenvectors. In this step, we'll take all the eigenvalues and we'll sort them in a decreasing order, which means from largest to smallest. And simultaneously, sort of the eigenvectors accordingly in matrix P of eigenvalues. So the resultant matrix will be named as P. We talked about what is an eigenvalue and the coefficients of these eigenvectors are known as the eigenvalues. So yeah, moving to the seventh step, that would be calculating the new features or principal components. So here we'll calculate the new features. To do this, we'll multiply the P matrix to the Z in the resultant matrix Z. Each observation is the linear combination of original features. Each column of the matrix is dependent of each other. Last but not least, so remove lesser unimportant features from the new data set. The new feature set has occurred, so we'll decide here what we to keep and what to remove. It means we'll only keep the relevant or important features in our new data set and unimportant features will be removed out. So coming to the applications. So here you can see computer vision, representation, pattern identification, image compression, and face recognition. So, and also we have gene expression analysis, and its purpose is determine the core set of conditions for usable gene comparison. And there are many more: handwritten character recognition, data compression, etc. Coming to the conclusion of that. So PC, we all know that from what we have studied till now, we can say that PCA can be very useful when there is a severe high degree of correlation present in the multi-attributes. So when a data set consists of several clusters, the principal axis found by PCA usually pick up the projections with a good separation. PCA provides an effective basis for feature extraction in this case. So, and for good data compression, PCA offers a useful self-organized learning procedure. Moving on to that, let's discuss about the shortcomings of the PCA. PCA requires to diagonalize matrix C heavy if n is large. PCA only finds linear subspaces, and it works best if the individual components are Gaussian distributed. Example, ICA does not rely on such a distribution. And principal component analysis does not say how many target dimensions to use. So that's all. Thank you for listening. I hope you understand.